Welcome to this explainer. If you've been following climate tech, you already know that integrating renewable energy is basically the engineering challenge of our generation. But right now, there's this massive, unexpected twist happening in how artificial intelligence actually manages our global power grids. Behind the scenes, we're seeing this fascinating battle between two very different types of AI, both competing to keep the lights on when the weather gets rough. It's literally a classic David and Goliath story, but played out in algorithms.
Okay, let's look at this massive surge in renewable energy we saw in early 2025. Just look at the numbers from the first half of the year. Solar generation leaped by an absolutely staggering 43%, and wind power jumped 16%. I mean, this isn't just incremental growth, it is a total structural transformation of our energy grid. But with that incredible growth immediately comes a much higher stakes game for grid stability. Think about it. The more we rely on the wind and the sun, the more we rely on accurately predicting exactly what the wind and the sun are going to do. So, to really understand this coming AI showdown, we've broken our journey today into 6 logical steps. We'll hit the renewable energy boom, the extreme weather problem, benchmarking the unknown, AR versus NAR models, the robustness gap, and finally, why less is actually more. Let's kick things off with Section 1, the renewable energy boom and its incredibly high stakes. For decades, grid operators relied on highly predictable thermal plants, right? Coal and gas. You put fuel in, you get an exact amount of power out. But renewables are wildly intermittent. We're seeing a 27% combined jump in wind and solar in just a single year. And what's really wild is that this massive influx actually pushed traditional thermal generation into a 2% decline over that exact same period. So we're crossing this threshold where the grid's backbone is now heavily reliant on meteorological whims, which means the AI models forecasting our power supply, they have to be absolutely flawless.
But as our reliance on these sources grows, we run straight into Section 2, the extreme weather problem, and frankly, a fatal flaw.
The existential threat here is extreme weather. Climate change is making intense storms, heat waves, and erratic winds the new normal, and that exposes a super dangerous vulnerability. The crucial point here is that our current AI forecasting models look completely fine on average sunny days. You look at their standard error metrics and they appear highly accurate. But this totally masks how fragile they are when a sudden storm hits. An AI that is 99% accurate on a calm Tuesday is completely useless if it catastrophically fails during a torrential downpour, leading to massive grid instability and potential blackouts. There's this quote straight from recent energy research that just perfectly captures this. It states, "Grid stability depends not on average case accuracy, but on a model's ability to anticipate abrupt ramp downs." We simply can't afford AI systems that only work under low-stress conditions. It is exactly those abrupt ramp downs, like when thick storm clouds suddenly cover a huge solar farm or turbulent winds force turbine shutdowns, that actually cause grids to fail. We desperately need systems that thrive in chaos. To fix this blind spot, researchers built an unprecedented stress test, which brings us to Section 3, benchmarking the unknown with the R2 energy framework. Now, what's really fascinating here is the sheer massive scale of the R2 energy benchmark they use to test these models against high-impact tail risk events. We are talking about over 10.7 million high-fidelity hourly records pulled from 902 different wind and solar stations. This isn't just theoretical sandbox data. This is real-world, hard-hitting operational data. By leveraging totally diverse climates, from coastal plains to arid highlands across 4 distinct regions in China, and focusing specifically on extreme labeled events like rainstorms and heat waves, this dataset really sets the ultimate stage. It allowed researchers to pit more than 16 state-of-the-art AI architectures against each other, and they were measuring not just theoretical error rates, but actual industrial safety compliance. So let's meet those contenders in Section 4, AR versus NAR models. We're primarily looking at 2 distinct families of artificial intelligence here, autoregressive models, or AR, and non-autoregressive models, or NAR. You can kind of think of the simpler AR model, things like GRU or LSTM networks, like navigating a storm step by step with a compass. It takes the weather data, makes a prediction for the next hour, updates its position, and then moves to the next. Whereas the massive NAR models, specifically those highly complex transformers that totally dominate the tech world right now, they try to process the entire horizon simultaneously. They look at all the data at once. It's like they're trying to memorize the whole map before even stepping outside.
This brings us to the real climax of this explainer, Section 5, the robustness gap
and the ultimate stress test. Let's see what happens during extreme weather. Power generation just shifts drastically away from the norm. If you look at how the median power output behaves, a heat wave actually causes wind power to drop due to stagnant high-pressure systems, basically a wind drought. Meanwhile, rainstorms introduce wild turbulence and massive variance. The physical environment just completely changes its underlying rules. First off, the researchers noticed something they call the clear sky paradox. During heat waves, which, by the way, are critical grid events because everyone cranks up their air conditioning, it turns out it's actually incredibly easy for both AI types to predict solar output. Why? Because a heat wave is a low entropy event. The sky is completely clear, the weather is stable, and there are no clouds. So both the simple AR and the complex NAR models do great, but that creates a really false sense of security. But look at this staggering collapse during high turbulence rainstorms. When the weather becomes highly chaotic and entropic, the complex transformer entirely fails. It scores a negative 78.57% forecast skill score. That means it performed significantly worse than a basic physics-informed baseline. Meanwhile, the simpler, step-by-step AR model, the GRU, thrives, boosting performance by 40%. The Goliath was completely blinded by the storm, while David navigated right through it.
This catastrophic failure under stress reveals what the researchers coined the robustness gap. It basically proves that simply throwing more mathematical parameters, more layers, and sheer algorithmic complexity at a problem isn't always the answer. Under real-world pressure, what actually matters is how smartly a model integrates dynamic weather data, not just how massive its neural network is.
So we have to ask ourselves in our final section, Section 6, why less is more and the role of physical causality. Why exactly does this simpler, David-sized model beat the Goliath? Why is less actually more in renewable energy forecasting? Well, the AR model wins because its underlying design perfectly aligns with the physical reality of how a storm actually unfolds in real time. Power generation during a storm is a causal, stepwise reaction to immediate, local weather forcing. Because the AR model processes data sequentially, injecting new weather data at every single step, it perfectly mirrors this physical causality. It adapts to the storm exactly as the storm evolves.
In contrast, those massive NAR transformer models kind of suffer from their own ambition. By trying to look at the entire weather horizon all at once through global attention mechanisms, they end up suffering from signal dilution. They look at sudden, violent wind turbulence and interpret it as mere noise. The model mathematically smooths out the data to find a broad pattern, entirely washing out the crucial, sudden, real-time drops in wind that actually cause grid blockouts.
And then there's the final cost-benefit blow, which is pretty staggering. Transformers are exponentially more computationally expensive, resource-heavy, and slower to train. Yet, during the absolutely most critical moments on the grid, they deliver vastly inferior accuracy compared to the highly efficient, lightweight AR models.
As we wrap up this explainer, the critical takeaway from the source material is super clear. Navigating the renewable energy transition safely demands that we focus on extreme turbulent conditions, not just sunny days. And when we do, we find that alignment with physical reality is a much greater advantage than sheer mathematical complexity. Sometimes a highly complex AI is actually an operational liability if it doesn't fundamentally understand how nature works. It really leaves us with a fascinating paradox to consider for the future of climate tech. In the tech world's relentless rush to build bigger, heavier, and infinitely more complex artificial intelligence, have we accidentally forgotten that nature itself still operates sequentially, just one step at a time? It's definitely something for all of us to think about as we build the grid of tomorrow. Thanks for joining me on this explainer, and keep questioning the data.